Okay, so let's discuss synchronous generators. Synchronous generators are basically AC generators. Um, they produce AC voltage, AC current, and synchronous generators are usually three-phase generators. They are also called alternators. The basic idea of synchronous generator is the same as we discussed in the three-phase system. If you remember, we discussed single phase, two phase, and three phase generators when we were discussing three phase systems. So the basic idea is the same, that we again go back to chapter number 4 and the DC generators. If you remember, DC generators are basically AC generators, and there's a commutator that converts AC into DC. So the idea remains same. That is, you have an armature, which now for DC generators, what we studied is you have an armature which is rotating, and you have magnets which are providing magnetic flux. Now the rotating armature interacts with the flux, and according to Faraday's law of electromagnetic induction, the flux changes, and the voltage is induced in the windings of the armature. So the idea remains same. The only difference is most of the synchronous generators, the winding, armature winding, where the voltage is induced, as we discussed in the chapter of three-phase systems, those windings are on the stator. That is, those windings are not moving, those are not rotating. What is rotating is the magnetic field, the flux coil, the either the electromagnetic coils or the permanent magnet coils. Those are rotating. So the end result is same. When the coil rotates, magnetic flux changes its value, which is which interacts with the windings that are not rotating, and the value still changes. And when the value of the flux changes, those voltage is induced in those windings. Now, why we choose to have three-phase windings where the voltage is induced on the stator? Uh, the biggest reason is for the commercial power generation, the voltage and the current. The voltage that is generated is at a very high level, and when the load is connected, the current, of course, is very large. So in general, the power of the generator is quite large. As you can see, many of the generators, they can produce up to 1.5 gigawatt of real power. Now, when you have this much real power, uh, if you choose to put the armature winding on the rotating part, that means you need what? You need the carbon brushes, you need the slip rings, and with this much current coming out of the generator, you will have a huge drop at the slip rings and the carbon brushes. So it is not safe. Neither it is more efficient to choose the winding to be rotating when you are generating such a high current and voltage. So most of the time for synchronous generator, we choose the windings to be on the stator, where the voltage is induced, that is the armature winding, and we make the flux, the magnet, uh, to rotate and produce an alternating, or produce a time varying flux. Now, you can make a generator, synchronous generator, like the one that we studied in chapter 4, where the winding, armature winding was rotating, and the flux was produced by stationary magnets. But those generators, basically, they operate at a very low voltage and current. Hence, you don't expect a lot of voltage to be dropped at the carbon brushes or the slip rings. Okay, so why they're called synchronous generators? The reason is given right here. They're called synchronous generator because the induced voltage and the frequency of the induced voltage is synchronized or locked to the speed of rotation of the magnetic field. That's why it is called synchronous generator. And in the next topic, you will see what will be the frequency of the induced voltage and its relationship with the speed, which is F is equal to Np over 120. N is the speed of rotation of the magnetic field coils, electromagnet. If it is coils, then of course it's going to be electromagnet. P is the total number of poles, and 120 is to compensate for rotation per minute, since this is given in rotation per minute. So 1 minute is 60 seconds, and this 120 is to compensate for the minute into seconds in general. So look at this example. It is required to produce a frequency of the induced voltage to be 60 Hz using an 8-pole motor. How fast the rotor will be rotating? Simple example. Two things are given to you and the third thing is required. So the motor should be rotating at 900 RPM if you want the frequency to be 60 Hz, and there are 8 poles on the rotor. 8 poles means that there are 4 sets of north and south pole. So you have 4 coils or 4 permanent magnet, and each permanent magnet, of course, they have north and south poles. So one magnet has 2 poles. Let's look at what are the features of the stator. Stator is where you have your armature winding where the voltage will be induced. So very simple, very basic. It is cylindrical laminated core. Why laminated? Because we want to reduce the eddy current losses. That's why the core is laminated. So it's a cylindrical laminated core. You have slots, and your armature winding are in those slots where the voltage is induced. And remember, the 3-phase windings are insulated from each other. They do not have any physical connection with each other. Each phase will have voltage induced, and that voltage is going to be 120 degree apart from the other phases. The 3-phase winding is always connected in Y, and then the neutral is connected to the ground. Usually the nominal line voltage is about 25 kilovolt or less than that, but it does not exceed 25 kilovolt. And the reason it does not exceed 25 kilovolt, because it will be hard for the insulation between the 3 phases if the voltage is going to be very high. What are the features of the rotor, which is where the poles are? So again, the rotor depends upon what number of poles, how many poles are there, and that depends upon how fast your rotor is rotating, because you have to produce, let's say, a constant frequency of 50 to 60 Hertz, right? 50 Hertz in Europe, 60 Hertz in America. So when you have a constant frequency to produce, if the speed of rotation with the generation method that you're using, if in that generation method the speed of rotation is low, that means you need high number of poles such that your frequency will still be 60 Hertz. And if the generation method that you're using, a power generation method, the speed of rotation is high, then you need less number of poles to keep the frequency to be same 60 Hertz. So there are 2 types of rotors that are used for different power generation plants. Those rotors are salient pole rotors and non-salient pole rotors. So this is a salient pole rotor. That is, the poles are jutting out of the rotor. And you can have many poles in this salient pole rotors because they are not connected with each other. The poles are jutting out. So you can have many poles. Now, if you have many poles, that means to produce 60 Hertz, your speed has to be low, right? Because N times P is going to be constant. That means salient pole rotors are used where the turbine is rotating at a lower speed. And in general, they are used with the waterfalls, the hydro power plants, because hydropower plants, the turbine is huge, the rotor is extremely large, turbine is extremely large, and when the water falls on that, it rotates slowly. So to produce the same 60 Hertz, Even if it is rotating slowly and if you have more poles, it will still produce 60 hertz, 60 cycles per second for the induced voltage frequency. The other type of rotor is non-salient pole, which is basically like this. You have a smooth rotor, and then the poles are basically infused on that smooth rotor. Poles are infused on that smooth rotor. So you have, you can have one pole like here, two poles basically, one north south. You can also have one more pole on this side, but it is not very easy to infuse more poles because this is one piece. The whole thing is one piece, so everything is connected. So it is not very efficient, or it is not even possible to infuse more poles on this cylindrical rotor. So non-salient poles have less number of poles. Non-salient rotor has less number of poles, and it is used with the turbines that are rotating at a very high frequency. And generally, your gas turbine, your fossil fuel turbines, they run at a very high speed, and the cylindrical poles are used in those type of turbines. And in the next video, we're gonna discuss the circuit and the load on the AC generator.